So, in the last lecture, we have discussed about the de Broglie hypothesis and the story behind this great theory regarding the wave particle duality. In this lecture, we are interested to explain the experimental verification of de Broglie's hypothesis, which was experimentally determined by C.J. Davison, American physicist C.J. Davison and L.A. Germer, who were performed the experiment in USA. De Broglie's hypothesis was again experimentally verified by G.P. Thomson also, who performed his experiment in Scotland. Now we start our presentation regarding the experimental verification of de Broglie's hypothesis. So, de Broglie's hypothesis tells us about the wave particle duality, where the wave character and the particle character both are represented by this fundamental equation, which was established for any particle and for any wave. So here lambda is the de Broglie wavelength and the energy of recoil photon E is equal Pc, which is some h nu, which is equal to hc by lambda. So here the de Broglie hypothesis for photon is considered. We can apply this for electron also. So this was the hypothesis of de Broglie, which gives us the wave particle duality. This is described in detail in my previous lecture. If you are interested, then you can go back to previous lecture and see what was it is. Now American physicists C.J. Davison and L.A. Germer performed the experiment which determines the de Broglie hypothesis experimentally. So the experimental arrangement is shown in this figure, where electron from a heated filament F, which were collimated by a single slit system, were accelerated by the anode A having a small axial hole in it. The accelerated electron beam emerging through this hole was then incident on the crystal of nickel C. The electrons scattered by C in different directions were collected by Faraday cup D, and the scattered intensity was measured by a sensitive galvanometer G. The collector was so designed as to detect only those electrons which had the same energy as the incident beam, so that only the incident electrons elastically scattered by C were detected. By rotating the collector along the line about an axis to the crystal, it was possible to determine the scattered intensity in different directions. Now we will describe the experimental results. This was the experimental result. The result of this measurement, in which the scattered intensity is plotted as a function of the scattering angle in polar graph, in which the radius vector is proportional to the scattered intensity. the angle between the radius vector and this is the radius vector, the angle between the radius vector and the coordinate gives the scattering angle theta. The different curves in this figure were obtained with electrons accelerated to different energies by changing the accelerating potential between F and A. Between F and A. Where is A? So, at 44 volts, a small but distinct spark. At 44 volts, a small but distinct spark appears at an angle about 60 degree. The length of the spark increases at higher accelerating potentials and the angles at which it appears also changes. The spark becomes most prominent at 54 volt and the corresponding angle is 50 degree. At still higher potential, the length of the spark decreases until it disappears completely about 68 volt. So here we notice that the spark decreases. The spark decreases gradually as the anode voltage increases. Now the preferential reflection, not potential, the preferential reflection. If we minutely noticed this figure, the preferential reflection of 54 electrons at 50 degree scattering angle is an evidence of the diffraction of electron from the single crystal of nickel. As is well known, in a crystal lattice there are atoms or groups arranged in a regular array. For this reason, a crystal can be used to diffract X-rays which have wavelengths comparable to the space between any two consecutive layers. The usual diffraction relation is 2d sin theta is equals some n lambda, which is known as Bragg's law. For the maxima, then gives the wavelength lambda provided the atomic spacing d is known. Theta is the angle of diffraction at which the maximum occurs. Consider such a regular array of atoms arranged in a lattice. Sets of parallel planes having concentration of atoms can be drawn through the array in two dimensions. These appear as sets of parallel straight line as shown in the next figure. Let a beam of electron be incident normally upon the crystal face. The beam makes an angle phi with the normal to the set of the plane. Then, according to Bragg's law, here will be reinforcement of the de Broglie wave associated with the electron beam if the following condition is satisfied. What is it? 2d sin lambda is equal 2d sin psi is equal n lambda, which is known as the Bragg's law. Then, if d is the spacing between two consecutive atomic layers, then from this the d is nearly about 0.91 angstrom, and xi can be calculated from this. Xi equal to 180 degree minus 25 by 2 is equal some 65 degree. If we put the value in this equation, then we get lambda is equal some 1.65 angstrom. So if we consider the de Broglie's equation, then lambda is equal some h by p, which is equal to h by root over of 2 me, which is also equal to some h by root over of 2 mev. So if we place the value of h, me, m and e and the v, then we can get the value of lambda is 1.67 angstrom, and in the previous case we get the value about 1.65 angstrom. So from these two observations we can say that electron has also wave nature. This experiment gives the conclusion that essential correctness of de Broglie hypothesis. So from the Davison-Germer experiment, the essential correctness of de Broglie's hypothesis is established. Thank you.